All right, I think we can get started now that we've had our small dose of excitement this morning of getting the new projector to work. So this is going to be, I think, the last lecture where I actually am discussing material that you're going to be held accountable for. So this is homework assignment 5, and I'm going to add a little something to that just to fill things out. But starting next week, or starting on Thursday, in fact, we're going to have more guest lectures, including ones where I may be the guest, of giving you things that kind of give you some additional either culture or skills. So let me just mention one of them. Next Tuesday, Gunther Weber, who's a colleague of mine at LBL, who is also an expert on visit, is going to come down and give you a much kind of more comprehensive view and introduction to what visit is all about and what it can do. So that's next Tuesday. Next Thursday's lecture I'm going to cancel. And the reason I'm going to cancel it is that I will post this on Piazza. There is a hackathon next Wednesday and Thursday at LBL, which I'm not sure it's going to be something that you will be interested in doing, but I'll post a link for it, on a tool that's being developed by Intel, or has been developed by Intel, based on the roofline performance model. But as part of that hackathon, on Wednesday there'll be an introductory lecture about here's what performance models look like. Sam Williams will give part of it, and the Intel team will give part of it. I will send you both the, I'll send you the announcement, but there's going to be, it's not just going to be something you can do in person, but you can actually watch it on Zoom. So that's what we'll do instead of Thursday's lecture, which is a talk on Wednesday afternoon on performance models, essentially on roofline performance model. Let's see, while I'm figuring out other scheduling, the following week, the week of the 12th, 13th, week of the 13th is supercomputing. It's the big international meeting / trade show for high performance computing. And I will be at that on Tuesday, and class will simply be canceled for that. So there will be no class on Tuesday. And then Thursday, starting on Thursday again, we'll start having other guest lectures, and I'll be announcing those on Piazza as they come along. So I'll put all the scheduling stuff up tonight or tomorrow morning. All right, so any questions or comments? I'm happy to see, although it gives me a little bit of whiplash, all these emails with the subject heading milestone 1 coming in. Although I realized I used an unfortunate bit of terminology, even though it's standard. My day job is actually managing a large software project, and I'm constantly haranguing people about getting their milestones in on time. But you've all been wonderfully compliant on this issue. So what I'm going to talk about today is the final homework assignment, the performance assignment. And so I'm going to go through multi-grid one more time, and I'm actually going to add a little something from my research portfolio that may be of interest for those of you who are doing structured grid for your projects. So let me just remind you again, here's multi-grid V-cycle that you apply, that you compute you compute point Jacobi some number of times. If your level, you haven't reached the bottom level yet, you compute the residual, you average the residual down onto the next coarser grid, define a correction, and then apply V-cycle recursively. Then you come back up, interpolate your correction onto phi, and then phi you apply point relaxation some more times, unless you've reached the bottom and we're just using as a bottom solver just point Jacobi. We assume we can get down to a fairly coarse grid where point Jacobi converges fairly rapidly. So you do this at the top level, iterate until the residual is reduced by some large factor. Okay, so that's the algorithm. here's what your implementations are going to look like that you're going to get. So the homework assignment 5, you'll be given a working version of multi-grid and a test harness and build and everything else. However, it's going to be slow. And your job is going to be to try to make it faster using the pencil construction that we've talked about. So here's the baseline implementation, and what I'm going to talk about today is more the mechanics of how you organize yourself to do this kind of performance analysis and tuning. So here's your baseline implementation of your residual. This is just this guy here, just that one line. So we have a member function of multi-grid called residual, which takes arguments, there's some small errors here. Don't worry about them. That should be A_res, not res. You first set your residual to 0. Then you iterate over all the points in your box, in your domain. And then for each point in the box, you compute Laplacian, which first is done by computing the sum of the things that are offset from the current point, and that's done in a nice dimension-independent way by iterating over dimensions. And then down here, you take that, I did the wrong thing here. What I gave you, I said it was residual, but it was this point relaxation. So ignore this slide. It's structurally the same. What you do, though, is instead of this, I can just fix it on the fly. There. And yeah, I grabbed the code for, no, yeah, let's back up here, go to slideshow. And that's still not quite right because that's minus the residual. The residual is this. Minus plus okay, so to resume, this loop here and this line here is compute Laplacian. This line here, and Laplacian times h squared. I don't divide by h squared. This is multiplied by 1 over h squared times minus Laplacian plus right-hand side. That's your residual. It's a pretty straightforward implementation using the rectMD array indexing machinery. So what happens? How do we find out what happens? Well, I've already talked about timers, but there's one important thing that you may have missed because it went by quickly. So here's how you get timer output. There's already timers in multigrid, the multigrid that you will get. However, there's one more thing you have to do to get the timer output, which is to tell your shell that you want it. And you only have to do that once within a session. So the way you do that, and I have this in my .cshrc file, or you can put the corresponding things in your bash if you use bash into that file. There you have to export it. But what I do is I set an environment variable called ch_timer, and I don't have to. I can set it to whatever I want. It can be true. It can be false. It can just be set to blank. But what your program will look for, what the timer software that you have embedded into your into the code will look for, is a look to see if that environment variable has been set. If it does, it will generate an output. So, and I have here a little example. What you do is to make sure it got set, do print environment, and it'll either be set to something or it'll be set to nothing. If you see ch_timer there, and when you do print environment, then you're fine. Now, so we have the environment variable set. Now we run the code. And just to make things simple, I put the 3 lines of input into a little file so I can just redirect that into the input here. So mg2d.exe, that's what's generated by building multigrid. And one of the things you will get out, last line of the output to terminal, is the total number of flops. I'll show you what that looks like in a minute, because you may want to use more information than what I'm giving you from this. And then we look at the file time.table. So fine. Here's time.table. I've just taken a slice out of it. This is the call to, this is something I've labeled multigrid, which is actually kind of all of the multigrid calls aggregated together. And then I've timed separately vCycle. And as you can see, the little bit of aggregation I do for multigrid is not costing me that much. The fact that I'm calling a function here, because inside of vCycle it's the same cost. So function calls at this level of granularity are negligible. Furthermore, I've put timers into relax, residual, average down, fine, interp, those 4 functions that are essentially make up vCycle mathematically. And it produces times. So the question is, fine, it produces times. You only know the denominator here. You have to know a numerator. Well, to tell how you're doing. Well, we have the numerator here. The total number of flops in multigrid is something that I'm printing out for you. And for this particular problem, which was a 256 squared calculation, it was this many flops divided by slightly less than 1 billion flops, and slightly less than 93 million flops, not 1 billion, slightly less than 100 million flops. And then divided by the total time in multigrid, or in vCycle equivalently, 0.367 seconds, 254 megaflops. As I have said, from timing this thing, that's not good. That's what happens after my matrix multiply falls on the floor. So I want to be able to do better than that. So what I do is, now I'm going to try just improving one routine. And the routine I'm going to improve is residual. Why? Because even now that I fixed it, it is the simplest thing I've got. I know what Laplacian looks like. I know what adding, subtracting it, multiplying it by a scalar and subtracting it from the right-hand side looks like. Yeah, I'll just fix one other thing here. That's RES. That's I'm not changing phi. And I may as well fix these. No, I'll wait for that later. So I go in and I'm not going to show you how I did this, because that's what you're supposed to figure out for yourself in this assignment. So I went in and I replaced the baseline implementation of residual with pencils. Great. So what do I find? Well, I find that the time spent in residual is 0.0033 seconds. Well, how is that? Is that good, bad, or indifferent? Well, it's promising, because from my previous timing, it was 0.0203. Well, that's about a factor of 6 improvement. So if I was getting the same flop rate everywhere, I would be getting now something that's over a gigaflop. Yeah, that's respectable. Again, judging from the performance numbers we got out of DGEM. Now, that's great, except that we haven't really tackled any of the big pieces. We have to do the same thing for relax, certainly. Now, if we, just assuming that we're getting the same improvement in performance, if we knock down relax by a factor of 6, ignore the recursive call to vCycle, because that'll scale up or down, presumably with how we do at the finest level. So that would be if we knock that down by a factor of 6, that'd be 0.004 or 0.04. You know, that's looking promising, except that now what was started out as something small average down in fine interp would start to look relatively large. So let's see what that looks like. So when we re-implemented relax, we get with pencils, we get 0.0274 versus 0.2405. That's a big improvement. Now, if we look, though, at the total amount of time being spent for V-cycle, now that we've made relax much faster, we notice that, and then subtract off the part that is coming from the recursive call. So that's the amount on this level. That's about 0.05 seconds, 0.02 of which is being spent in fine interp. That's now not 20% of the time, that's about 40% of the time. Change that as well. So we probably want to get them if it's not too painful. So how does that going to look? So let's look at the baseline implementation of average down and see what we have to think about. Multi-grid residual. This is not residual, this is average down. Ignore that. As I said, I'm going to no. Okay, good. So what does that look like? Well, I have a box that's just, so in 2 dimensions, what is this box? This box goes 0, 0 to 1, 1. And then I have a normalization, which is 1 over the number of points in the box. So that's my normalization coefficient. So how do I compute an average down? Well, I iterate over the points in the coarsened version of the grid. So I have 2 grids, one fine, one coarse, and I want to average something from the fine grid to the coarse grid. So I iterate over the points in the coarse grid, and then so I take the residual, which is farther up above, the coarsened residual has been initialized to 0. Then the coarsened residual on a coarse grid point is incremented in this loop by the fine residual at twice this grid point plus the offset, where the offset is in one of this 0, 1, 0, 1. 0, 0 to 1, 1. So what's going on geometrically is that I'm taking, now think of this not as now being this kernel, but think of this as being 4 grid points that cover this coarse grid point. And what I'm doing here is in this loop, I'm taking this and incrementing it into that, this incrementing it into that, this incrementing it into that, this incrementing it into that. The way I'm accessing the data, it's a particularly simple data access, is that a point on the coarse grid corresponds to that point, a point on the fine grid that's given by twice the point on the coarse grid, double the all the indices, and then an offset going from 0, 0 to 1, 1. And then at the end, I normalize, because I've summed these things up, now I have to divide by the number of points to get an average. So this is telling you something about how you can pencilize it. You should be able to make this into a kind of pencilized nested loops, where instead of having the access to the right-hand side be stride 1, have the access be stride 2. So it's possible to do that. Again, I'm not completely telling you what's going on, simply because I want you to think through it yourself. So the other thing about doing the performance testing is that you need to know how you're doing kind of on a smaller scale. What I've outputted for you is the total number of flops spent in all the V-cycle calls. Now, in fact, you have more information as is. I could have outputted it on a per level basis, and in fact, I had it there, but I took it out. It's not very useful. But there is something else that in order to do this, let's go look inside a V-cycle and see how I computed flops. So I have a counter for each level called m_flops. And what I do is after every call of a major function in V cycle, I increment it by the number of flops that it took to execute that call. So here we are at the initial point relax. So I apply point relax. And how many flops got expended there? M underscore flops is incremented by the number of iterations I do in the relaxation step, the number of mesh points there are, and then the number of flops per mesh point, which in this particular case, to do point Jacobi, is twice the dimensionality of the problem plus 5. So in 2 dimensions, it's 9. In 3 dimensions, it's 11. Now, so if you trust me to have gone through the code and counted flops correctly, this is a useful piece of information. You could put, for example, in the member data for multi-grid, another counter, call it M underscore flops underscore point relax. And you could increment that counter just with this, and then you can access it or print it out afterwards. So similarly, you can do that for residual, for average down, for fine interp. Notice I've color-coded all of these so that you can see where for each one of them, where I've incremented the things by the number of flops. And that's, again, this one has, let me just fix my mistakes as I go along. So the information is here. I'll leave it up to you if you want to figure out, okay, exactly how many flops am I doing? Exactly what is the performance I'm getting when I do the performance improvement for each of these member functions separately. So then finally, there's kind of doing the performance squeezing. Part of it is going to be re-implementing it so that you use the pencil construction so that you're doing stride 1 accesses or small constant stride accesses at least, maybe stride 1, maybe stride 2, and doing arithmetic that's orderly based on that. However, if you want to either see what the compiler is doing or try to get the compiler to do something better, you can actually tell it that there are opportunities. So in Clang, so if you're running on a Mac, you're using Clang or Clang++, there are compiler flags that tell it, why don't you try to vectorize? And the compiler flag that does that in Clang++ is -r pass equal loop dash vectorize. Now, that will give you back messages from the compiler that says whenever a loop is vectorized that it has done so. And it will tell you the parameters of the vectorization. Now, if you want to know what loops are failing to vectorize and why, then there's another compiler flag in Clang, which is -r pass-analysis equal loop vectorize. And that, as it goes through the code, it's saying, well, I'm trying to vectorize this loop, here's why I couldn't. Now, similar things available in G++. The thing that does both force the vectorization and tell you what's going on and both why it's succeeding and failing is the flag -f tree-vectorizer-verbose equal 2. Now, there's something else you can do is in using G++ is you can force it to turn off vectorization and see if it makes any difference. Now, it turns out G++ for this particular application, at least for the versions of G++ I'm running, and on the platforms I'm running, G++ is more pessimistic about the value of vectorization. So it turns out that when I ran this on a Linux workstation I have access to up at LBL, compiler came back and told me, nope, we're not vectorizing this. We don't think it's worth it. Our performance model tells us it's not worth it. So it's not clear how much this will tell you, but you should still know about the possibility of A, getting it to give you the diagnostics, and B, seeing, okay, if it vectorized, no vectorized, doesn't make a difference. Now, one final thing is that you may go in, you may think you have done the pencil construction correctly, but actually, the compilers are not as smart as you would like them to be, and in some ways they are smarter than you are because they will see dependencies that your mind might not have caught. Here's an example of one that kind of caught me a little bit by surprise until I saw the compiler message. So here I have a set of pointers to doubles that I, down here in this ... have set to be the addresses of the beginning of contiguous chunks of storage. Fine. So here is a loop that I would have thought would have vectorized. It's the k goes from 0, goes up to some size, k++. A is equal to b times c plus d of 2 times k. So this is what I mean by a constant stride. When you're incrementing k by 1 and you're indexing by double k, that's the same as incrementing by 2 every iteration. And that is in this form, that is simple enough for the compiler to pick out and do something smart with. Now, this fails. It didn't vectorize, and the way I first saw it is the performance wasn't improving. So I turned on the diagnostics. I said, "What's going on here?" And it told me, "Oh, this header's I can't figure out what's going on in this header well enough to see if it's going to vectorize." And it's obvious why when you stare at it. I wrote it in a way that it was more obvious. Bar.size is a function call. It could be changing what the stopping criteria is at every iteration. So it turns out it's not in the case we're doing here, but I have to write it in a way that the compiler sees that it's not. So here's what I do. I say declare a variable integer high is equal to bar.size. And then I just write the loop, int k equals 0, k less than high, k++. This is the loop. Everything works. You get the high performance. You get the things that say that it knows how to do the right things. Loop bodies have to have obvious constant stride access and fixed loop limits, or in order to get the full benefit of what you can do with this. Now here's a question. If we replace double star ABCD with vector ABCD, that should have been, let's actually do this with correct syntax. So vector of doubles. Now, will the compiler recognize the unit stride access? I don't know. Here's the reason why it's an I don't know rather than a no. Some compilers actually know lots about STL. And one of the things you know about STL, it's part of the definition, is that when you are walking through it at constant stride or stride access, you're walking through contiguous data. So that's part of the specification for vector. Will the compiler know that? Beats hell out of me. Way to do it is to find this out is to actually try it. Now, if it doesn't, then it's actually possible for you to do something, which is to take take A of 0, the address of that, and assign it to some pointer to a double, and use those instead. The syntax will look the same. You'll get, but then the compiler it'll be totally unambiguous to the compiler what's going on. So that's kind of the guidance I'm going to give you for the programming assignment for number 5. That will be launched Thursday morning after you submitted number 4. It will be due a week from Friday, so that you'll have a week and a half to do this. And the ground rules will be in the write-up for the programming assignment. Questions, comments? All right. So the last thing I'm going to talk about is a piece of associated research/development that we are doing. Let me get rid of that. So let's go back Let's go back to our multi-grid. So our multi-grid is, this is V-cycle. Look, nice high-level mathematical specification for this, easy to read. So at the level, in fact, how does that translate into code? Well, at the level of V-cycle, let me go back here and show you V-cycle. Here's V-cycle. At the level of V-cycle, there are all these calls to all these things which are incrementing counters, but if you kind of ignore those things, yes, you have point relaxation, point relax, residual, average down, recursive call, interpolate, point relax. It's pretty much the same as this, modulo the fact that it's not some nice equation formatter, but ASCII text. However, once you lift the hood up and start looking at the actual code for this, it looks a little messy written in the baseline form, and when you write it with pencils, it's going to look even messier. And when you start doing things like threading and various kinds of parallelism, it will get messier still. So the question is, can we do better, just at the level of structured grid arrays? So the answer is, yeah, we're trying to. Oh, one more thing. Using Fortran only helps this marginally, and in fact, it doesn't help it at all. The code that you have to write if you're using a standard Fortran is, has it has indices all over the place. So it's not even as, in some ways, it's messier than what we do. It has a few advantages in that we don't have to make up things for multidimensional arrays, but that's looking like less and less of an advantage as we go forward. So can we do better than this? And here's how we're going to do that, or at least going to try. One of them is to identify programming abstractions as aggregate operations corresponding to the high-level mathematical representation. Second thing is, once we have those abstractions, implement them as C++ classes, but have the implementations of those aggregate operations contain the optimization that you would otherwise do by hand. The idea is that the opportunities for obtaining high performance don't really come from looking at low-level code, but come from the mathematical structure of the algorithms in the first place. The fact that pencils work comes from the fact that you're looking that they're worth doing. Comes from the fact that you have a multidimensional array and one implementation fact which you're stored in a row major fashion, and that you're doing things that are stencils. So the third point, which is in parentheses because that's the thing that makes this kind of researchy, is that there are compiler technologies that we can take to something like this. This strategy here is called embedded domain-specific language. It's a domain-specific language in the sense that we're taking structured grids and we're essentially writing a language in which it is easy to express structured grid operations. It's embedded. That refers to the fact that we are implementing this as a set of classes in C++. It's perfectly legal C++, and you can run it anywhere. However, there is the opportunity to apply source-to-source translation, various and other compiler technologies, to make this even better. Now, in fact, we've done half of this already, and that's what RectMD array does. It was defined high-level data structures for structured grids. Now, in fact, what I did is I took RectMD array out of the larger project, stencil project that we've been doing, and I'm going to expose to you the stencil project, the other half of the RectMD infrastructure, which is a stencil language. This is joint work with Brian von Strahlen and Chris Gebhardt. So, what are stencil operators? So you have some rectangular array, which we think of mathematically as mapping from a box to Rn. And then a stencil operator, L of phi, is something that gives you something else. It's another array defined on B prime, a different box. And L of phi at a grid point I is the sum over some finite set of grid points S, A sub S, phi of I plus S, where A is independent of I. It's just a collection of numbers that are as big as S. What does this look like for our Laplacian? For Laplacian, it's 1 in all the unit directions away from 1 in all the unit directions, plus and minus, and then minus 4 times the dimension, minus 2 times the dimensionality of the problem for S equals 0. So these are very familiar objects to you. Now, we can think of the operator L as an object that acts on any rectMD array. So instead of thinking of this as something that's intimately tied to phi, which is kind of how you program it, you can instead say, okay, L has a life of its own. Mathematically, it certainly does. I've written it that way. I've written it as an operator. Well, let's be explicit about what that operator looks like. L is the sum over a set of points in some finite collection of points in the d-dimensional integer lattice. And it's for each one of the points in this set S, I have a coefficient, and then I have a shift. So S superscript S bold, S superscript S bold applied phi of I is equal to phi of I plus S. So all I've done here is I've said I've written this as an operator. It's a sum of elementary operators. Those elementary operators are translations of your grid by S. So stencil operators have their own algebra. You can add them, compose them, multiply them by scalars without knowing what they're going to be applied to. So let's say I have two stencil operators, L1 and L2, and these have each their own set of coefficients, and for simplicity I'm assuming that they're defined over the same set. You can always arrange that by setting some set of the coefficients to be 0. And now, what is the composition of L1 and L2? Well, I can write that as a sum of shifts, sum over T, and I haven't specified what that set is. You can compute it. And what are the coefficients? Well, it's the coefficients are given by the sum S plus S prime is equal to T of A1 of S, A2 of S prime. And that's so you have an algebra for stencil operators, and that's a convenient thing to have because it tells you how to build up complicated ones from simple ones. So how can we realize this in programming? So I'm just going to tell you what the API looks like. So we have a class. It's parameterized by something. The something is the value of the coefficients. So stencil of double, so these are going to be double value coefficients. M_Laplacian, so this is my second order Laplacians. So how would I build that? Well, I would start by initializing this as to be the diagonal term. So this is the stencil of double, and this is probably, I did this, I changed my mind how I wanted to do this, so let me, yeah, okay, back again. So I have an auxiliary class in this called shift, and it's just the thing that, given a point, produces something whose semantics are shift by that amount. Now, if I multiply a shift by a double, or by a member of this class, then I get something that's of type stencil. So this is a way of getting a shift by nothing. So that's the identity operator, but with a coefficient that's 2 times the dimensions. So that's, and I did something else that was wrong here. So this is the diagonal term of Laplacian. And now down here, I'm just building Laplacian in just the same way I would build it if I were applying it to some function, except I'm building it in terms of these shifts. So I have I loop over directions. I get the unit vector in the d direction. I have a stencil plus, which is 1 times the shift in the positive direction of E, and then I have minus, which is 1 times the shift in the negative direction. So those are shifts by 1 plus or minus unit vector with coefficient 1. And then I increment Laplacian 2D as Laplacian 2D plus minus plus plus. This constructs an abstract object, a stencil, that is the same stencil we've been using for Laplacian 2D, except I have it multiplied by 1 over h squared. And there are some reasons that you might not want to do that. So let's take this and see how does residual change when I do this. So this is actually code I grabbed out of my working implementation of multigrid using the stencil tools. So I have res 5 right hand side. I left the timer in there. I grab the box. I set the ghost cells. I compute 1 over h squared, and then residual is initialized. So I'll tell you what these symbols mean in a moment. These are obscure symbols. So let me tell you what one of them is. So this says this is an operator, bar equals. It takes what it does is it says take what's on the left hand side and stuff into it what you get from applying the stencil to phi over a box, and then you multiply overall by a scalar. And the scalar happens to be minus 1 over h squared. So this computes minus 1 over h squared times Laplacian. So that's most of the way there for my residual. And then the important thing I wanted to emphasize is that part of what you have to specify, and you have to do this a lot and be careful about or have sensible defaults in doing any kind of aggregate structured grid operation such as stenciling. You have to say where you're going to compute it. And here we have a nice place to park that information. We have it as one of the arguments to the apply stencil operator. So then down here, this illustrates another feature that we like to have, which is just an algebra for multidimensional arrays. I'll talk about that in a moment. But this looks like this is what it looks like. I'm taking this multidimensional array and adding to it on a point-by-point basis, right-hand side. So that's what residual is, and it looks very much like how you would write it down mathematically. One other thing about stencil operators can be strided, both on input or on output. So if you want to iterate over a set, and you want to say, I want to take values on a coarse grid and deposit them into values on a fine grid, or I could have incremented them. I could use plus equals here as well. I would take our source to just be all ones. But here I would take our des to be, let's say I wanted it on a factor 2 finer grid, to be 2s. So this is, again, what I'm doing here is very much in the spirit of stencils, except that you have, instead of unit access, you're incrementing what you're depositing into by some constant non-unit access. Our dest is a tuple, is a point. And you can also do offsets, which you need to do if you're trying to fill up this whole array. On top of that, we need to do arithmetic and a little more on rectMD arrays. So here's an example. I just showed you that. A res is plus equal to a underscore right-hand side. That's defined on the intersection of the two D boxes, the domain that the box over which this is defined and the box over which this is defined. Now, there's a much more general version of this that you need to be able to do when you're doing, particularly when you're doing nonlinear problems. And that's pointwise operators. And this is A notation. It's an ancient notation from kind of functional programming, where we define an operator to have a function that applies to the space of values that that an array takes on. So let's say u was real valued. This would be a function that takes as an argument a real and returns an argument that's real. So how do you promote such a function to act on arrays? Well, this is f applied to an array u, evaluated at I. That's equal to f of yeah, I did that wrong, and now I'm not going to be able to fix it. The subscript I should be on the inside. So that should be f of u sub I is, so you're taking for each value u sub I, you're taking f and evaluating it at that point, and then stuffing it into an array at that location. It's pointwise operations. So we have a programmatic interface that does that for all f of u, so this is where I'm putting it. This is where the array I'm inputting. This is the function I'm using, the thing that corresponds to f up here, and this is the box over which I'm doing it. And what does this do is that this, first of all, what is f? F is going to be a function of an input and an output that corresponds to what the value space is of u and what the value space is of f of u. So this takes a function that's just a function of two variables and promotes it to a function that's a function of arrays, of corresponding pointwise function over arrays. Now, the other thing is that for a lot of applications, you want to have want to be able to do this. You may have functions that, for example, take an array as input, produce an array as output, but you also have parameters that are independent of the array. For example, time step is a common one that is just a fixed number. So what you would like to do is have a function that takes three variables, the value of the output at a point, the value of the input at a point, and a function, let's say it's time step, and use the same machinery for this. Well, there's a very nice way of manipulating partially evaluated functions called lambda calculus that's implemented now as part of the C++11 standard. So here's how we use it here. For all f of u, u, so again, this is the output array, this is the input array. What corresponds to a function here? Well, this expression here is a lambda expression that says, take this function, evaluate it at this value here, and think of it as being a function that takes that takes these two arguments. And then we evaluate it over the box. Another place where this is useful is if you want these functions, you want them to be member functions of a class, then again, this is actually grabbed from another piece of code that's running. This is an Euler code. And this step here is I'm actually taking a set of conserved variables, mass, momentum, and energy, and converting them over an array of those, and converting them to an array of density, velocities, pressure, primitive variables. And this is via a member function called const prim. It's a member function of the Euler operator class. So how do I do this? Well, so here's my output array, here's my input array, here is my function. Why am I using the lambda? Well, const prim is a member function of the place where I'm sitting. And the thing about member functions is that they carry a context with them. In some sense, you can think of a member function as having whatever arguments are in the argument list, plus another argument. And the other argument is a pointer to who you are, is this. And the way that this is reflected in lambda calculus is that square bracket this is the square bracket in lambda calculus in general are the variables that you want to carry along as context for evaluating this. Here, the context you need is all the member data from your member function. And why would I need that? Well, for example, I need the equation of state gamma. that would be stored in my member data for the class, and then applied over a box. So this is the kinds of things you do with when you're doing these are typically for nonlinear problems. I've also slept over another piece of detail here. What are the value types that are being taken here? Well, it turns out that we have to kind of incorporate them from the start into RectMD array. So RectMD array takes on, remember it had these other template parameters, or at least one, which was the number of states. And what these functions are things that take on the type of, we call them tensors, and they are the type of the it looks like, in this particular case, looks like a vector of length whatever. But it certainly acts like it syntactically. So, in all of this, how do we get performance? So, in the apply functions, we implement the pencil construction. So let me go back here. What does the innards of this thing look like? It's calling a function. It is a function. So what does it look like? Well, when you drill down and look at what's happening internally, here's what the code looks like. And again, I just cut and paste this out of the existing code. So you loop over all the points in the stencil, and then for each point in the stencil, I create a pencil. I've already defined the pointers. I've also, this underscore I refers to the fact that there's another loop outside that may be over components. So I get the reference to the phi, I get the reference to L of phi, and these are just constant increment 1, stride 1 accesses inside of this loop, k equals 0 less than n points test, k plus plus. And then I take L of phi plus equal coefficient of phi val. So it's exactly what I've done already by hand in the multigrid code, except for one very important fact. I have done this once, and now I can use it on lots of different stencils. So let's see, how is the performance? We said how I got it. How is it? So this is actually, again, I've run this on this laptop and measured the performance. So here's what I get. So if I look at, so this is V-cycle, it's 0.077 seconds. And let's compare this to the baseline. I think, again, that's an error. I believe that is, no, I think that's right, actually. I'm not going to fool around with that. So compared to the baseline, which is 0.347 seconds, so I'm getting a substantial improvement on the order of a factor of 4.5 over the baseline. However, it's not quite as good as what I got by hand. And if you look at the actual flop rates, we get about 1.2 gigaflops from the stencil, 1.7 gigaflops by hand, and then the baseline is, as I said, 268 megaflops. So a couple of comments on this. This is respectable. I am willing to give up 40% in order to get something that I can do quickly. And if I really feel like that 40% is painful, maybe I'll go back and do the by hand sort of things to get that last little bit. However, there's another hidden advantage, not so hidden advantage, to using stencils that maybe make it worth having the last 40%, is that it's more productive. It's actually more productive in the sense that the number of lines of code to achieve a certain functionality is actually fewer than in the baseline. That's because we are manipulating and using higher order constructions. We are not doing things a grid point at a time. We're doing things a whole grid at once. So let me illustrate that by saying, here's all of the innards of multigrid on a single slide using stencil. So here's residual. Here's what the actual things that do the calculation look like. Residual is m underscore Laplacian 2d, so that applies Laplacian multiplied by minus 1 over h squared, and then increments that by the right-hand side. Point relax. Here's my iteration over the number of my loop over the number of iterations. I set the ghost values. There's an actual identity operator in that I'll talk about in a second, where that came from. But this is just initialize this with the right-hand side times minus the relaxation parameter. And now we increment that by another operator applied to phi, which is Jacobi. And I'll show you how I computed that. And then I copy, I will correct my mistakes as I go along. No, that's actually right. That's not a mistake. Play from the current slide. So L of phi is a temporary. The way Jacobi is organized is that I actually compute the full Jacobi operator and then overwrite phi with it. And that's what I'm doing here. That's copy 2. Fine interpolates taking and doing piecewise constant interpolation of a correction onto phi. That's just a loop with a one-line body. And it means for every point in that little 2x2 box, it goes the other direction. I'm incrementing it by a source that looks like delta. Average down, again, there's just a single stencil that does average down, period. Now, the other thing about this is that for a lot of these stencils, I've realized, oh, I have them. Why do I need to rewrite them all the time? I can just put them in a library and they'll be available for me. So we have such a library. So this is the list, this is part of the list of implemented stencils. It'll give you some idea of what we're doing. Is that we have an identity stencil, that's the trivial identity calculation, derivatives of various orders and various centerings. Here's the Laplacian 2. These strings are ways of accessing the library. So the library is a dictionary and uses map. So here we go, various things that take you from various centerings to other centerings, edge to cell, cell to edge, something that the operator that appears in divergence calculations. So how do I use these things? So here's this is a object of type stencil library, stencil lib, and I just call get and give it a string. Laplacian, my second order Laplacian's already in there, done. Similarly for average down, already in there, done. Now I didn't have laying around a point Jacobi operator, but I will soon because this is something that comes up in pretty regularly. So I will put that into the library. Similarly for interp, I will put the interpolation, the array of interpolation operators into the library. Here I just computed them. So, so let me summarize here. What have we learned? What have we talked about today? One is, again, to repeat something I've said several times in the course of the semester. Small constant stride, constant stride, that should be constant, small constant stride access. Let me get rid of that. Such as stride 1 and vectorization make a big performance difference. The factor of 5 to factor of almost 7, that's a big deal. You don't want to, it makes a difference when you're running a large calculation, particularly as soon as you start doing 3D, you see the difference. The second thing is that you will find that doing this by hand is drudgery. You'll do it once for this assignment. You will try to find ways of not having to do it. And one of the things you should learn is that higher level abstractions can actually make it easier. It can enable performance engineering by making your performance enhancements reusable. whether you build it as a library that you've implemented high-performance Laplacian once, and you will do it over and over again, or you do something like this stencil stuff that we now have made into a library, the thing that evaluates any stencil. The other thing that this does, it allows you to improve performance without rewriting large amounts of application code. So one of the things that is a concern is that, yeah, I have this very nice, I've done a good job on performance on my laptop. Now I move to a supercomputer, how is that going to work? Or in fact, this laptop, which is now close to 5 years old, I buy a new one. And it has more vectors, it has lots of things. What happens? Well, if you hide the details of things through abstractions, then you're going to, if you have chosen the abstractions carefully, you'll be able to re-implement the implementations with a lot less work than if you had just done monolithic code, big pile of code that had everything optimized kind of in a flat fashion. Now, I'll leave this out here as an advertisement. The stencil library that I just talked about is available for use in structured grid projects. Anyone who wants to use it, if you're feeling adventurous, we will be happy to provide it and support it. In fact, it's gotten a fair amount of exercise. We've implemented solvers, we've implemented Euler solvers, so that means a lot of the nonlinear and time-dependent stuff. We have a pretty good idea of what both its performance is going to be and what its and have a very strong sense that it's correct. So drop me an email if you're interested, but you will not get it until after the last assignment is due. All right, well, maybe not, actually. I'm perfectly willing to let you see it, but you have to implement the last assignment by hand. All right, I'll stop here. Any questions? Go ahead.
Do you know what the last bit of performance from by hand versus the stencil, what that comes down to?
I'm trying to figure that out. I know, okay, there's an interesting thing. Well, the interesting thing is that for stencils, it's about 60%. You get 60% of the way. It's a 40% difference. For pointwise operations, it's also about 3/4. It's about comparable. But there, we understand what the problem is, that for all to work, you have to assume that inlining is going to be sufficiently aggressive and that it will do the right thing and interact well with the compiler. It appears not to do that in such a way that we can use macro expansion with for all to get that last 25%. For stencils, I've been fooling around with all sorts of things for the last week to try to figure out, is there something we're missing? And I haven't come to a good conclusion yet. It probably will require us to do something that I don't want to do because I'm not good at it, which is to look at the generated assembly code to find out what's going on. Yeah?
Kind of a follow-up.
Yeah.
So how compiler dependent is this then? Because it seems like it depends a lot on how aggressive.
No, because because I'm essentially doing the same thing as if I'd done this by hand. It's as good as you will get by hand because it's the same strategy. Express everything in terms of 1D accesses to 1D contiguous storage. Other questions? All right, good. So as I said, I announced at the beginning of class, I'll announce again. Next Tuesday, we will have a guest lecturer, Gunther Weber, who will talk about a more in-depth view and comprehensive view of Visit. He's an expert on it. And then instead of next Thursday's class, there is a lecture, a set of lectures on performance modeling that will be available on Zoom on Wednesday. I believe it's 12:30 to 2. And I'll post all the links for that in the next couple of days. All right, good. Thanks.